Good morning. Welcome all to the session of Computer Organization and Architecture. Today we will be discussing Module 4 concepts. So Module 4 is the memory system, okay, and before starting with the actual topics, we need to have some basics, okay, which we require in order to understand how the memory works, okay. So first initially we will discuss about the basic concepts of the memory, and then we are going to discuss about each of the individual memories. And in this module we are going to discuss how the memory structure is organized in a computer system, and we are going to discuss different types of memories, okay. So we have DRAM, SRAM, we have virtual memory, and we have cache memory. About all this we are going to discuss in this module. So if you consider memory structure, it is very difficult to understand because it is a very complex structure. So let us understand by initially considering the fundamental structure, or we can say it as a basic structure of the memory, and then we will consider a detailed structure, and we will understand the individual types of the memories in detail. And now coming to the basic concepts, so we know that all the programs and data that are used by the computer are stored in the memory. So whatever the values we want, or whatever the instructions we write, everything will be stored in a space called as memory. It is the basic function unit of a computer system. So it is a very important part of the computer system. So all the data and the programs are stored in the memory. And next, so if we consider the memory, so we want the memory to be fast, we want the memory to be large, and we want the memory to be inexpensive. So because if you consider the computer system, if the cost of the system is considered, so we want the computer system to be cheap. So it is nothing but, so we consider the functional units which are present in the computer system. So if they are cheap, then overall cost of the computer system will be cheap. But if you consider the execution time, if you consider overall performance of the computer system, then we know that most of the computer the program execution involves data transfer between the memory and the processor. Therefore, so if you consider the speed of the system, it is going to affect the overall performance, overall speed of the system. Therefore, we want the memory to be fast. And if you consider the programs which are large, and if the data required data set is too large, then we want large memory, so that the large program which are executed are loaded into the memory. Therefore, so we require all the memories or the memory functional units, whatever we have, we require the memory to be fast, and we require the memory to be large, and the same time we require the memory to be cost, that is, we require the memory to be low cost. So if you consider the hierarchical structure of the memory, so you can see here, so the fast and expensive. So if you observe, so this is the hierarchy of the memory. So we have at the base we have offline storage, tape, and then we have the magnetic disks, so secondary storage, then we have main memory, then we have cache, and then we have registers. So this is the hierarchy of the memory elements or memory, what we use in a computer system. And here, so you can see here, so increasing performance and increasing cost. So with the increasing performance is nothing but the speed, speed of operation. So with the increasing performance, so there is increase in the cost also. Therefore, it is impossible to achieve all the three. So what are the three factors? We want the fastest device, we want low cost device, and then we want large device. So these three are impossible to be achieved simultaneously on or by using a single device. So because of the factors associated with the cost and the performance. So now you can observe, as one goes down the hierarchy, so there is decreasing in cost, so then increasing capacity, okay, increasing access time. So capacity also increases because registers are able to store only one word length of the data. Okay, so then if you consider the cache, it is very small. Even though it is fast, okay, it is very small, and the capacity is low. And then next, main memory. So compared to cache, main memory will be large, but compared to the secondary devices and offline storage devices what we connect externally to the computer system, so main memory is also small. So like that, so if you okay go down, so it decreases okay the cost per bit and then increases the capacity and increases the access time. See the speed, okay, what we were speaking. So if you consider okay the base, so it is the slow devices. Okay, as we move on to the base of the okay triangle what we have written, the speed also decreases. So then decreasing frequency of access of the memory by the processor. So it is nothing but, so we know that usually registers, okay, the data are moved into the register so that okay the processor makes use of the registers in order to achieve high performance. And also we know that, so if you have a segment of code, so which is to be okay frequently accessed, so then that will be stored in cache memory in order to increase the speed of the memory. So this is how okay so the hierarchy of the memory exists. So we cannot have the speed, we cannot have okay low cost, and we cannot have the high capacity, okay, so all in one. So we have to compromise one for the other. Okay, so next concepts which we need to understand is about so how the memory is organized. So how do we access the memory, and then so what are the different memory okay address assignment schemes we have. So all these concepts we have already discussed in the first module when we considered okay the different functional units of the computer. There itself we have discussed about the addressability, and also we have discussed about how okay the memory is organized. So we will okay have a recap on it, and then we will move on to the next topic. So next let us see okay how the memory is organized, and so what are all the okay assignment, that is address assignment schemes we have. Yes, next, so maximum size of the main memory is determined by the addressing scheme. So here the addressing scheme, so depending on whether you are using 16-bit for representing the address, or you are using 20-bit for representing the address, or you are using 32-bit for representing the address lines, okay, so the maximum size of the main memory varies. So for example here I have written, so a k-bit address memory has 2 to the power k memory locations, so namely 0 to 2 to the power k minus 1 called the memory space. So if you are using a 24-bit okay memory, so 2 to the power 24, that is equal to 16 mega locations, okay, memory locations will be there in the memory space. So if you are using 24-bit memory. Similarly, if you consider the 32-bit memory, then 2 to the power 32, that is 4 giga, okay, 4 giga, so addressable locations will be there in the memory space. And so if you consider 2 power 10, so you can see, so 2 power 40, so 1 tera, like this, okay. So depending on the address lines, okay, depending on the k value, so we will be having so many addressable locations in the memory space. So the maximum size depends on the depends on the addressing scheme, okay. Yes, next we have most computers are byte addressable. So we have discussed this already. So each and every location, if you are using a 32-bit computer, okay, then the first address, if you consider, if it is 0, then the next address will be 4, next address will be 8, like that. So the address is a byte addressable, okay, and you will be having okay the addressing format, so which I will be showing later, okay. So next is memory consists of many millions of storage cells, each of which can store 1 bit of data. So each and every cell is able to store 1 bit of data. Usually memory is made up of the transistors, okay. So the transistors are able to store either 1 or 0. So depending on okay the value, so it is able to store 0 or 1, therefore it is made up of millions of the storage cells. So Next, when we consider individual, that is SRAM, DRAM, we will see so how will be the memory cell and how it is going to store a value, that we will discuss in the next sessions. So just understand, so it consists of many millions of storage cells, and each storage cell is capable of storing a bit of data. And next, data is usually accessed in n bit groups where n is called word length. So we know that individual bits will not be accessed in any of the computer. So only when we consider certain registers where we have to read some condition, or depending on some condition where we have to take some decisions. So in such cases we are going to check for a particular bit in a register, or some flag bits will be checked for determining some conditions. Yes, except those, so we are not going to read or write single bit of data into or from the memory. Usually, so we are going to read or write n bits of data, and those n bits, group is called as word length of the computer. So the minimum bits actually that are written or read from the memory, read or written from the or into the memory in one memory access cycle, is the definition of the word length of the computer. So next, if you consider the next point what we have is to retrieve information from memory either for one word or one byte. Addresses for each location are needed. So if we have memory, since we have to copy the data into or from the memory, we need to have address locations for each and every byte, or for each and every word we can say. So we should have address for all the bytes so that we can access the data. So these are all the basics we need to have. And next, so if you observe, as I said, so this is how the memory segment will be there. So in a computer system, so if you consider this memory segment, so let us assume, so this is 0, this is the address of the first word is 0. So this is the first word. So next is the second word, like that we will be having ith word, and lastly we will be having the last word of the memory. And if this is 0, so we know that the address space varies from 0 to 2 to the power k minus 1. So you will be having 2 to the power k total bits, total capacity or total memory space. So if you consider the address for the first one it will be 0, for the last one it is 2 to the power k minus 4, not minus 1. So it is the range, but if you consider the address and if you assume it is a 32-bit computer, then the last word will be having an address of 2 to the power k minus 4, that we have seen in the first module. So next, if you consider the word, so as I said, we are considering throughout our discussion a computer having 32-bit word length, because that is the standard at present. Therefore, so if we consider the computer is having 32-bit word length, then so how we are going to name the bits? So bits will be starting from B0, so next bit will be B1, next B2, etc. So we will be having B30, next B31. See here, so that is given in this figure, and you can observe, so MSB will be usually a sign bit. So next, if you sign bit, we know that if you have a positive number then it is 0, if you have a negative number then it is 1. So next, if you consider the ASCII character storage, if you have the same 32-bit word length computer, and in 32-bit we know that ASCII characters are binary codes, so which have 8-bit of length. So each character will be having 8-bit binary value. Therefore, so if you consider 32-bit word length computer, then so in 32-bit 4 ASCII character can be stored. So you can observe so how 4 ASCII characters are stored. So next, as I said, so all the computers or most of the computers, instead of saying all, most of the computers are byte addressable computers. So what is byte addressability? So if you consider the addressing, so byte locations have addresses, so 0, 1, 2. So if word length is 32-bit, they have Yes, sorry. So byte locations have addresses 0, 1, 2, etc. Okay, and if the word length is 32, so their successive words are located at addresses 0, 4, 8, etc. So if you consider 0 in that word, you will be having bytes 0, 1, 2, 3. Okay, 4 bytes will be there, and so each word will be having an address of 0, 4, 8, etc. Okay, so the last word will be having an address of 2 to the power k minus 4. So it is impractical to assign distinct addresses to individual bit locations in the memory as we discussed. So we are not going to write or read one bit of data into the memory, therefore it is impractical to assign address to each individual bit. Therefore, so we are not going to assign address to individual bit. So instead what we are going to do, usually we read or write a word of data, in n bit, a group of bits, so which is actually n bit, and which is referred as word length of the computer. So we are going to read or write, we are going to retrieve or we are going to write a word of data into or from the memory. Therefore, so it is necessary to have an addressing scheme, so wherein we have a byte addressability, because so in some of the programs or in some of the applications it is not necessary to access the complete 32-bit word. Sometimes we may require to access byte. Therefore, so what we are going to do is we are going to assign address to the byte, and that scheme is called as byte addressability. So we are going to address the bytes as 0, 1, 2, etc. But if you consider 32-bit computer, so each word will be having addresses 0, 4, 8, etc. So within word we will be having addresses to individual bytes. If you consider 0, so there you will be having 4, as we saw in the previous, that is ASCII, character storage what we discussed. There you can observe, so we have 4 characters. So if you are representing the word address as 0, so byte addresses that are there in that particular word are 0, 1, 2, 3. So the 4 addresses will be there within one word address. So like that they will be having the successive word addresses, and so within that you will be having byte addresses. So in some applications, so if you are representing a byte quantity, so usually addresses are in terms of the word quantities, and in some application program, if you are representing or if you are referring to the byte addresses, then so you can observe, so the last 2 bits will be containing which byte is involving in that particular operation, that is read or write or whatever it is, which particular byte is involved, that will be given by the last 2 bits of the total word, that is the total address. So whatever the 32-bit address that will be provided, so out of 32-bit, so first 30 represent the word location, whereas the last 2 bits out of 32-bit represents so which byte of that particular word is involved in the processing. So if you are performing read operation, so the processor will read all the 32 bits or all the entire word, and it is going to consider only the last 2 bits for the processing. So whereas if you are writing, then if you are writing a byte, in that case, so the memory control circuitry has to take care that so the other bits whatever we have are not altered except the byte which is involved in the operation. So only that byte has to be changed, and other bits has to be kept as it is without changing its value. So that should be taken care by the control circuitry, that is memory control circuitry, which is present in a computer system. So this is about the byte addressability. So next we can observe, so what are the schemes we have. So addressing schemes, so we have big endian and little endian assignments. So what is big endian? So big endian is nothing but lower byte addresses are so used for the most significant bytes of the words. So if you observe big endian assignment, see here, so for the okay, MSB of the word. So if you consider this as the word, okay, you can observe this is MSB and this is LSB of the word. So in this case, lower byte is used for representing the most significant bytes of the word. So then we say it is a big endian assignment, and the processors like 68000 makes use of this big endian assignment scheme. And next, if you observe the little endian assignment, so you see here, so the opposite ordering, in the sense lower byte addresses are used to represent the lower bytes of the word. See here, so lower byte addresses are used for the less significant bytes of the word. So in a word, okay, if you consider, okay, the MSB, if the lower byte addresses are used to represent the MSB, then it is a big endian scheme. Whereas if you consider, okay, the little endian scheme, in little endian scheme, the lower byte will be used to address the least significant bytes of the word. Okay, so next, if you consider, so this is how, okay, the memory assignment, address assignment scheme will be there. And if you consider the little endian assignment, so usually the Intel processors what we have, they make use of little endian, okay, assignment scheme. And the ARM processor or controllers what we have, so they are, okay, they can be configured to use, so either of the two. So they can be configured to use a big endian scheme or little endian scheme. Okay, and there is no difference between, okay, the memory structure. Memory structure remains the same. So in any memory structure we can have, so either of the two. But as I said, as I gave an example, so Intel is making use of little endian assignment, whereas the 68000 what we have series, okay, the processors, they make use of big endian assignment, and ARM processors or ARM controllers what we have, so they can be configured to use either of the two. Okay, so this is about the assignment schemes. And then, so if you consider the connection, so this we have seen already in the first module. Okay, so how the CPU and main memory are connected, and there we have a diagram, so which is a bit, okay, different than this, but the concept is same. So here we have the processor, okay, and memory, and if you observe, we have two main registers that are actually, okay, used to communicate between the processor and memory. So these are the two which are used to establish the communication between the processor and the memory, and the registers are memory address register, and the second one is memory data register. And if you observe carefully, memory address register is having k bit length, whereas the memory data register is having n bit length. So the memory address register, so we have discussed, so that represent the total, okay, memory space. So 2 power k, so what we have, so that is going to give you the total, okay, addressable locations of the memory. So next we have data. So data, depending on the processor or, okay, processor used, so we will be having the data word length. So if you consider the word length, so in each of the memory location, so you will be having a word length of, okay, n bits. So now we have another signal here. There's another, okay, connection between the processor and memory, and that is the control lines. And if you observe, so in the control line we have two signals written here, read or write bar, and next we have MFC. So here read or write bar to indicate, okay, whether the data is to be read or written. Okay, so then we have MFC. MFC is nothing but memory function complete, okay, completed, memory function completed signal, so to indicate that the operation is over, whether it is a write operation or whether it is a write operation or read operation. So once the operation is completed, so this will be asserted so that the processor can know, okay, the function has been completed. And so this control line can also be used to, okay, indicate how many dates, how many, okay, bytes of data needs to be transferred. So that count can also be, okay, given through this control line. And so sometimes in order to, okay, indicate whether there is successful, okay, transfer of data between the processor and memory, so even that can also be, okay, indicated by using this control lines. So yes, all these, okay, connections what we have, address bus, data bus and control lines, so all are, so, okay, present on a bus. And whenever there is transfer of data, so the n bit of data will be transferred, okay, so over the data lines what we have in a bus, and next, so the address of that particular data will be, okay, assigned or given over the address lines what we have in a bus, and depending on, okay, the operation control, okay, lines or control signals what we have, they will be asserted or deserted. Yes, so let us see how the processor is going to perform read operation. So now initially what happens is, so since it is a read operation, remember the control line, okay, so read or write bar whatever we have, that has to be set to 1 so that the read operation is performed, and so the address where, okay, or from where the fetching of the data has to be happen will be placed over this MAR, okay, over the memory address register, and so the processor is going to initiate by placing the address of the, okay, data which is to be read over this MAR, and then so it is going to set read signal to 1, read or write bar signal to 1, and the, okay, so from memory, depending on the, okay, address of the location, from that location address will be read, okay, and that will be, okay, placed over the MDR, the data. So depending on the address, the data will be read from the memory and that data will be placed over the MDR. So this is how, okay, and once this is over, once the fetching action is over, the MFC, so that is memory function complete, okay, completed, so that signal will be made high, so that, so it indicates the processor that the, okay, function is completed, okay, read operation is completed. And so if you want to perform, okay, write operation, then so it is going to, that is the processor is going to send the address as well as the data, okay, over this, that is address will be sent over the MAR to, okay, where the data has to be written, and that data will be sent over the MDR so that it writes the data into the memory, and the control lines, that is read or write bar, will be made as 0 so that write operation is performed. So this is how, okay, the read or write operations will be performed in a computer system. So we can, if you consider a read operation, we can say that, so it is the time between read and MFC signals. So we know that read signal is assigned, okay, to initiate the read operation, and MFC signal is, okay, asserted after completion of the read cycle. Therefore, so you can say that it is the between the read and MFC signal. So this is, okay, about the memory access time. And next is memory cycle time. So memory cycle is nothing but the time, okay, between two successive operations, two successive read or two successive, okay, write operations. So if you consider the time between the two, okay, successive operations, so that is called as memory cycle time. And usually, so this will be slightly longer than the memory access time. So memory access time, okay, will be smaller compared to the memory cycle time. So, and next, an important design issue is to provide a computer system with as large and a fast memory as possible within a given cost target. So that we have discussed, okay, at the beginning, that we need to have, okay, a fastest memory and largest memory, and at the same time we want the cost to be less. So in order to incorporate all this, so we are going to discuss, okay, about how apparently we can increase the size and the speed of a memory system, okay, keeping the cost less. So if you consider the caches, okay, so if you consider the cache memory, it is the fastest memory but smallest memory. Using, okay, cache memory along with the main memory in a computer system, we can, okay, apparently increase the speed, okay, of the computer system. And if you consider the virtual memory, okay, with the help of virtual memory, we can increase the size of the memory. We can increase the size of the memory using the virtual memory concept, okay. But physically there will be only that much of memory which is, okay, available, but virtually we can, okay, increase the size of the memory, or we can say that apparently the size of the, okay, memory can be increased, and that is how we are going to increase the space as well as the speed of memory by keeping the cost as same, okay. And Next, if you consider, as I said, the several techniques to increase the cost, the effective size and speed of the memory are cache memory and virtual memory. So cache memory, so it is used to increase the effective speed, and next virtual memory, it is used to increase the effective size. So how I said just now. So cache memory, so we are going to use cache memory to store the frequently used data, or the currently being used program segment and required data will be stored in the cache, so that the speed of operation is increased. So it is not necessary to fetch or have data transfer again and again from the main memory to the processor. Instead of that, so this cache will be built in such a way that so it is nearest to the processor, it will be between the processor and the main memory, and sometimes cache will be present on the chip itself, that is it will be present on the processor chip itself. So in that case, the speed of the operation will be increased. So then if you consider the virtual memory, as I said, so here what we are going to do is, so as we discussed till now, so whatever we write in a program, the addresses whatever we mention, so we assume that they are the physical addresses, but it is not true always, because in some cases the address or the actual physical address of the data which is being used may be different than the address which is specified in a program. So we might be using virtual address concept, so where we'll be having a memory control circuitry which will be mapping the actual physical address to the virtual address, or virtual address will be mapped into the actual physical address. So you can extend the virtual memory to as large as the actual memory itself. So whatever the space we have, memory space, to that extent we can increase the space or the capacity of the virtual memory. And in that case, so it is essential to have an additional circuitry wherein we have mapping of the correct addresses from virtual to physical. So in physical memory we will be having the data stored, and as I said, and in virtual memory, so we can extend it up to the maximum space which is available in the main memory. But so usually what we are going to do is, so while execution of a program, only a part of virtual memory will be active, and that part will be mapped onto the main memory. And so you can map it to the external device also. So virtual memory, whatever the data which we have, so that can be stored in the external devices also, so that we can map virtual memory onto the external devices. But as I said, since only a certain part of virtual memory will be active at a given point of time, it is essential to map correctly to the page required. So otherwise it may take longer time to map into the correct address, so that may decrease the overall performance or speed of the memory operations. So carefully we have to map whichever the page is required from the main memory or the other memory what we have, so that there is no considerable delay in accessing the required data from the memory. So this is about the basics what we need to understand about the memory. So in the next classes, in the next sessions, we will be discussing about the different types of memories what we have practically in a computer system in detail. Thank you for listening.